The topic of this video is tools for studying geometric growth. Most of the macroeconomic series that we study display geometric growth, so it's useful to have a few simple tools to deal with those kinds of series. Let's begin with a comparison of arithmetic growth and geometric growth. So here's an example of a series that has arithmetic growth. We say that some variable y as a function of time is equal to, say, 100 plus 4 times the index of time, which could be, say, years. Let's say we have a series instead that displays geometric growth. This series is equal to 100 times 1 plus 0.04 to the power t. So this is like the compounding that we've been talking about. So let's compare the values of those series as time progresses. So they both start with the value of 100 at period 0, as you can see from the equations if you put in t equals 0. And in fact, at t equal 1, they're the same as well, 104. By the time we get to t equal 2, they're just slightly different, 108 for arithmetic and slightly bigger for geometric. But we could see as time goes on and t gets bigger, say t equal 10 or t equal 50, they're really starting to look quite different. And in this case, even though the arithmetic and geometric series started out at 100, the geometric series is ending up at much higher values. We could also show it on a graph. So this graph shows the arithmetic series time path, and that's the lowest one. And then there are two time paths above that, the geometric, which corresponds to this equation, and the relevant exponential, which has the same growth rate. Notice that the exponential and the geometric have very similar paths. The reason is that the exponential growth rate is simply the same as the compound growth rate that you get with the geometric series, but the compounding is done instantaneously. So just remember that there's a lot of similarity between geometric and exponential. One is simply the limit of the other. So quiz yourself. Suppose we have our arithmetic and geometric series, but I've made one change here. I put it so that the arithmetic series starts at 200 rather than 100 at time equal to 0. So the question is, what would you expect to happen to the difference between the arithmetic series and the geometric series as time goes on? Well, the difference will decrease over time. In fact, the geometric series will eventually overtake and pass up the arithmetic series. And that's easy to see by either plugging in values or by looking at the graphs I showed you on the previous slides. Let's think about more general equations and properties of arithmetic versus geometric series. So to make sure we understand the notation, if I write something as delta y of t, what I mean is the value of y at time t minus the value of y at time t minus 1. So with the arithmetic series, where we have, it starts at some b, which is just some constant when time is equal to 0, plus a times the value of t, then the change in yt, if it's arithmetic, is always going to be a. So we're going to have a constant change in levels. The increment to y will always be that constant a. Now let's take a geometric series where we've made it more general than the specific examples. In this case, y is equal to b times that compounding factor, 1 plus g to the t. Well, in this case, the percent change in y is going to be constant and is equal to g. So geometric series exhibit a constant percent change. So here's a useful transformation for geometric growth. Ln denotes the natural logarithm, and if you think back to your math classes, that means the logarithm where you use base e, and e is that very special number that's equal to 2.718 plus lots of other digits. If y of t is growing geometrically and g isn't too big, then we have the following relationship. The log of y of t then is approximately equal to the log of b plus g times t, where g is the growth rate. So what we've done is taken a series that grows geometrically, and if we take the log of it, it's going to look like a linear series with respect to time. And also the change in log of y of t is going to be approximately equal to the percent change in y, and that's going to be equal to the growth rate. So taking the log, we turn something so it looks like it's a linear function of time, and that its change becomes the percent. So here's an illustration. Suppose we have a series y of t is equal to 60 times 1 plus 0.05 to the t. So the growth rate is 5%, 0.05. If we graph y of t, it shows your standard geometric growth. This is against time on the horizontal axis. What if we graph log of y of t? That's shown on the right-hand side. When we graph log of y of t, it looks like a straight line. And in fact, the slope is equal to the growth rate. For example, if you look at between time period 0 and 20, you can see that log of y goes up from 4 to 5. So that change on the vertical axis is 1, and the change on the horizontal axis is 20. 1 divided by 20 is 0.05, and that's the growth rate of y. To show how useful this is in practice, let's look at the Dow Jones Industrial Average. This is a graph of that stock price index back to 1895, and this clearly shows geometric growth. Now, if we look at this graph, and suppose we're trying to ask the question, how bad was the stock market crash of 2009, which is shown in that last shaded area on the chart, how bad was that compared to the stock market crash in 1929 and through the Great Depression? Well, if you just look at the level of the series like we're doing now, it makes it look like the stock market crash of the Great Depression was hardly anything. It's just a little blip on this graph, whereas you have this huge decrease during the stock market crash in 2009. Well, the problem is that this really distorts the picture, because what matters to investors is the percent change. And since we were starting at a much lower level in 1929, we can't really compare the percent change to what it was in more recent times. Well, it's very easy to transform this variable in a way that makes it much easier to compare, and in particular, the transformation we just talked about. Let's take the natural logarithm of this variable and then graph that. In fact, this website I use, the Fred St. Louis website, lets you do that when you edit the graph. So now I'm showing you the natural log of the Dow Jones Industrial Average Index. Notice that this looks much more linear. Of course, there are a lot of blips along the way, but it's much closer to a line than the previous graph. Since we know that the slope and the change in this line is almost the percent change, that means we can start comparing returns across time. So now, if you compare the stock market crash at the beginning of the Great Depression, starting in October 1929, going through the early 30s, and then you compare that to the stock market crash during the most recent recession, 2009-2010, you can see that the stock market crash of 1929 was much bigger than the stock market crash more recently. And taking logs of that Dow Jones Industrial Average lets us make this comparison on the same chart. Finally, here's a really useful rule for thinking about how long it takes things to grow when there's geometric growth. In particular, there's something called the rule of 70, and it says that the number of years it takes for the level of a geometrically growing variable to double is approximately equal to 70 divided by the annual percentage growth rate of the variable. Now that might sound a little bit complicated, but the rule is very simple. Suppose the GDP per capita of a country grows at 1% per year on average. Then how long will it take GDP per capita to double? Well, the rule of 70 tells us to take 70 and divide it by that growth rate, which is 1. So we take 70 divided by 1, and that tells us it will take approximately 70 years for GDP per capita to double. So quiz yourself. Suppose another country has 5% average annual growth. Then its GDP per capita will double in how many years? 14 years, because we take 70 divided by that growth rate, which is 5 in this case, and we get 14. So, to summarize, we did a comparison of arithmetic versus geometric growth. We figured out if we take the natural log of a series with geometric growth, the slope of the line is approximately equal to the growth rate. The change in the logarithm of a series is approximately equal to the percent change in the series itself, so it's a really useful approximation to percent change. And the rule of 70 is a nifty approximation for calculating how long it takes for a variable to double.